All right, so today we are taking a look at linear and non-linear systems. So the first thing we need to just talk about is, so far we've just been looking at linear systems, really. We threw absolute value in there, which has linear parts to it. But today we're going to take a look at quadratics and what square roots do when we start adding them to our systems of equations. So if you take a look at this, there are three different types of solutions we could get when looking at quadratic linear systems. Let's represent them graphically. So we could get two solutions if we have a parabola. Opening up or down, it doesn't matter. But then we have some line just cutting right through that parabola such that it's intersecting at two different spots. That's how we could get two solutions. There's a couple instances where we could just get one solution. So again, we draw this parabola. And if we have a vertical line going straight through a parabola, that is going to give us an instance of just one solution. Another instance would be if we had a horizontal line coming straight through our parabola like so, and it's just touching right at that vertex. That would give us another instance of just one solution. And then the last instance we could get is if we have a graph of a line such that we draw the line and it just kind of taps the parabola at one singular spot. So right here, this line is just tapping this parabola right in there somewhere. This line is actually called a tangent line. The horizontal line would also be a tangent line because it's just skimming the graph like that. So both of those could be considered tangent lines. Down here where we get no solution, or sorry, on the next one, we would draw a parabola. And then a no solution graph would just be that line is somewhere on this plane, but it's either underneath the parabola so it never touches, or it's just like outside of the parabola. You could draw it in a couple different spots here. Same instance could be if it was opening down, right? You could have a line that's just right above that parabola on the same plane. Okay. So let's take a look at what this actually looks like if we add some math to it. So this first equation right here, I know we haven't seen this equation very often, kind of a blast from the past, but this equation is a line specifically in point-slope form. And the reason it's in point-slope form is because I give you a point, so this 2 and this 4 are showing us a point on the graph, specifically the point 4, 2. It's always the opposite of the sign that shows up in there. And then the slope comes from the value that is in front of our parentheses would give us the slope. And in this case, there is nothing right there, which means there's a 1, because 1 multiplied by a value just gives you out that value. A lot of people get confused and think that 0 is right here, but if you had 0 times a number, this whole side would just become 0. So we have a 1 right out in front of that. So let's just graph that line. To graph the line, we're just going to graph the point, which is 4, 2. So if we go to the right 4 and we go up 2, it gives us right here. And then if we graph the slope is 1, so it's going to take us up 1 and to the right 1. Or from our point 4, 2, you could also imagine down 1 and to the left 1 would also give us a slope of 1. So then we can graph this line now, going through here and through here. And then we have to graph the quadratic. So our quadratic is in standard form. Notice the hint here says find the vertex, which the x value of the vertex comes from negative b over 2a, so we'll start there. Negative 4 over 2 times 1 gives us 4 over 2, which gives us an x value of 2. Then to find the y value, we just plug that x value right back in. So if we have 2 squared minus 4 times 2 minus 2, that gives us 4 minus 8 minus 2, which, what is that? Negative 4 minus 2 gives us negative 6. So our vertex is at 2, negative 6. And then we can graph that. So we go to right 2, down 6, puts us here. And then from this, we can just graph our parabola. Luckily, right here, we have a value of just 1. So that means from this vertex, it's just going to look like the parent function. So if I'm thinking about my parent function, x squared equals y, and then just build my little table right here. If I went to the right 1, and I plugged that 1 into x squared, it would give me out a value of 1. So if I go to the right 1, it should go up 1. So we'll go right here, right 1, up 1. And then the next value that would be nice would be 2. So if we plugged in a 2 squared would give us out 4. So that means we'd go to the right 2 and then up 4. So right 2, up 4, 1, 2, 3, 4, puts us here. Was that 4? Yeah. And then we can just graph to our across the axis of symmetry is going to put us right here, and then right here. I'm off. Why am I? Oh, wait, sorry. Not right there. Right here when I graph that. And there we go. We see an intersection point right here between our parabola and our line. Hopefully you can see that this graph is going to continue in an upward direction like this. So the goal is to find where is it going to cross that line up here. So we really need one more point. So let's go one more further. If we plugged 3 into our equation, we get out 9. So we go right 3, 1, 2, 3. It's going to go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Puts us right here. And there we can see our second intersection point. So if we graph this thing, it's going to look like this. Comes down through our vertex and then comes back up. And it crosses that line in 2 different spots. So our solution to this system is going to be 0, negative 2, that first point that we found. And then the second point that we found is at 5, 3. So there's our 2 answers to our system right there. If we scroll down, we can see that this next one is actually graphing a square root graph. Again, we have our point slope form right there. This point that we get is an x value of negative 2 and a y value positive 1. So if we graph that, we're going to go negative 2, positive 1, and then we follow the slope, up 1, right 2. Or you could imagine it down 1, left 2 would also give us that. So it's going to look just like this. Just like this. And then to graph a square root function, you have to remember that, hey, this right here is the transformation. It's telling me left 2 and then down 1. So we can graph a point right there. Left 2, down 1 is going to put us right here. And then we need to think about our parent function. So the square root of x is equal to y. That's our parent function. I'm on my xy table. The hardest part about square root is thinking about nice numbers to plug into it. So like if we have the square root, I'm thinking, okay, 1 is a really nice number to plug in because I can take the square root of 1. That would just give me out 1. This time we do have an a value though. Our a value is 2. So we have to multiply our y by 2 because that a value is making it stretch. When we vertically stretch something, we multiply the y's because y is vertical. So that tells us 2, which tells us if we go to the right 1 on the graph, it should go up 2. So we'll go to the right 1 and we'll go up 2. That puts us at a point right here. The next easiest value we need to plug into this thing is 4. The reason we pick 4 is because the square root of 4 also gives us a nice number. It gives us out 2. So then again, we multiply by the a value, which gives us a value of 4. So when we need to go to the right 4 and then up 4. So we go right here, 1, 2, 3, 4, and then up 4, 1, 2, 3, 4. And there it looks like that's going to crash into our graph right there. From this point, we can imagine it going away from the line. So we don't need to see if there's any crossing going on up there. And then if we just connect these points together, we can see that this square root graph is going to just skim at one single point right there. And so this solution only has 1, and it is at 2, 3. Okay. Taking a look at this next one, now we're getting into solving algebraically. It says use substitution to solve the following system. So we can see that this quadratic is already set equal to y, so we can just substitute that right in to our equation on the top. So then we can say x squared minus x minus 6, and then plus 6 is equal to 2x plus 2. Because we have a quadratic, the only way to solve this is by either completing the square, quadratic formula, or factoring. And the only way to do that is if our equation is set equal to 0. So let's do that. We're going to set our equation equal to 0. We have x squared minus x. The negative 6 and positive 6 are going to cancel. And that's equal to, let's distribute the 2 right here. So 2x plus 4. And then we can set this equal to 0 pretty easily by subtracting the 2x and subtracting the 4. The reason I moved to the left side is because I want to keep that x squared positive. So then we got x squared minus 3x minus 4 is equal to 0. And this one actually factors really nice for us. It's x and x. Negative sign on the end tells us positive and negative. Because we're negative in the middle, I'm thinking 4 is going to be negative, positive 1 is going to be positive, and that gives us x values of -1 and 4. Unfortunately, once we get those x values, we're not quite done yet because the y values are going to give us points, right? We have x, but we need comma y to give us a point that it's intersecting. So what we do is we just take these x values, we just plug them right back in. You can pick either equation, it doesn't really matter. Let's take and plug into our quadratic because it's already set equal to y. So that'd be -1 squared minus -1 minus 6. So that's 1 plus 1 minus 6. Which gives us -4. So then there's one of our solutions. These solutions do end up being real. So we're at -1 comma -4. And then for our other solution, we'll plug in 4. So that's going to be 4 squared minus 4 minus 6. So that's 16. -4 and -6 make -10. So 16 minus 10 gives us 6. So our other solution is at 4 comma 6. And there's our two solutions to this system. Come down here, very, very similar question. This one, I'm just asking you to think about the quadratic formula because it doesn't factor. You could do completing the square if you really wanted to, but I always think quadratic formula is a little bit quicker. So when we go here, we're x minus 3 equals x squared minus 2x plus 1, right? I just took this x minus 3 and plugged it in. Set this equal to 0 so that we can use the quadratic formula. So I'm minusing the x and adding the 3. So that gives me 0 equals x squared minus 3x plus 4. Now we can quadratic formula since it's in standard form. So that's going to be opposite of b plus or minus square root b squared minus 4 times a times c, all of it divided by 2 times a. And that is going to equal our x value. So this equals 3 plus or minus square root 9 minus 16 over 2, which is 3 plus or minus the square root of -7 over 2. We now have a square root of a negative value. This is telling us we're getting imaginary numbers. Okay, so instantly right now we can say, hey, we're getting imaginary numbers. So when we're talking about the solution to this system, there aren't any real numbers that are going to come out of this because we're going to plug imaginary numbers back into our equations, would give us more complex numbers. So then really, when we're talking about this and we get a negative inside of a radical, we can actually stop right there and say there is no real solution to this problem. So we're just going to say no solution and call it a day. Scrolling down to this one, this time I put the equation in slope-intercept form, the kind of form we see all the time. So we can graph that one pretty easily. It's going to be a +2 as the y-intercept. Follow a slope of 3 over 2, which means up 3. 1, 2, 3, right 2. Puts us right here. And then we can just graph that line. You could also follow it down 3. 1, 2, 3. And then to the left 2 would put us here. And then so we can graph this way as well. And there's our line. If we're graphing this absolute value graph, hopefully we remember that h and k are the vertex. So we could say this is 2, 5 as a vertex here. So 2, 5 puts us right here. And then this 3 over 2 is telling us the slope going away from the vertex. And then the negative sign tells us that the absolute value is opening down. So I just need to follow this slope, 3, 2, in a downward direction both ways. So then I'm thinking down 1, 2, 3, right 2. And also down 1, 2, 3, left 2. Puts us here. And so then we can graph this absolute value graph. This is another special case scenario that we're going to see right here. Because if you see, we have a bunch of overlapping right here. And these are lines that are going forever in this direction. So this is actually an example where we could get infinite solutions for our answer here. This is not like a quadratic because a line and a quadratic could never line up like this. I actually skipped a question early on right here that said, could there be a quadratic linear system with infinitely many solutions? And the answer is no. And the reason is that lines have constant growth, while quadratics do not. So because there's a constant growth rate versus not a constant growth rate, like I said, it can't line up like this absolute value graph does. Okay, Scrolling down to the last little part of this, just a bunch of solving algebraically here. If you take a look at this problem, right here we got y equals x plus 2 and y equals 2, absolute value x plus 1 minus 2. Again, we can just set these equal to each other. All of these linear, nonlinear systems are going to use substitution for solving. So we got x plus 2 is equal to 2, absolute value x plus 1 minus 2. In this case, to solve an absolute value, you actually have to isolate it. So we're going to move the 2 over to this other side and say x plus 4 is equal to 2, absolute value x plus 1. Now we can divide both sides by 2 to get x plus 4 over 2 is equal to the absolute value of x plus 1. Now that it's isolated, we can split it into its two cases. There's a positive case that's going to come out of this, and there is also a negative case that's going to come out of this. The positive case is going to be the left side always stays the same, so x plus 4 over 2. And then the right side of this absolute value is just going to stay x plus 1. The negative case is going to be x plus 4 over 2, but then the right side is going to be negative, so negative x plus 1 when we do that. And the reason being because it doesn't matter if you plugged in positive or negative into this absolute value, it's going to always come out positive. So we have to imagine, well, what if our x plus 1 was negative? It should still equal x plus 4 over 2. And now we can solve both of these for x. So x plus 4 over 2 is equal to x plus 1. I would start by multiplying this 2 because in order to solve for x, we're going to need to get access to this x right here. So we need to get rid of the fraction. That gives us x plus 4 equals 2x plus 2. Now we can easily get the x's to one side, so minus x. I'm going to minus the 2 to the left side in the same process here to get 2 is equal to x. Once we get 2 equal to x, now it's just about plugging it back in to find the y. So y equals 2 plus 2, so y equals 4. So then our solution here is 2 comma 4 for our positive version of the absolute value. Negative version is going to do the exact same thing, so we're going to go x plus 4 over 2. I'm going to distribute this negative right away so we can just see that negative distribute. So that's negative x minus 1. Again, multiply the 2 first. That way we can free up the x plus 4 in the numerator there, so that's going to be negative 2x minus 2. And then again, I like to keep my x's positive, so I'm going to move the 2x here and then move the 4 to the other side. That gives me 3x is equal to negative 6, divide by 3, to get x is negative 2. And again, we take that, we could just plug it into our linear equation. So y equals, and then negative 2 plus 2, so we get a value of 0. So our other solution is negative 2 comma 0. These ones, you always need to check for extraneous solutions, as I noted right here. You need to check for extraneous. Honestly, you could just throw them in really quick. What you have to do is you have to just plug them into this equation. So 2 for x here, 4 over here. We have to use the absolute value equation because we solved for them in the linear equation. So when you plug this in, we got 2 plus 1 gives us 3. 3 times 2 gives us 6. Minus 2 gives us that 4. So that one's good. And then we could also try our other equation. So let's go negative 2. So we plug a negative 2 right in there. It gives us negative 1, but it's absolute valued. So this becomes 2 minus 2, which does give us out that 0 that we wanted for a y value. So both of these solutions actually work just fine. If you don't want to go through the little tediousness of plugging in by hand, you can always just open up Desmos, right, and throw both of these into Desmos. That's definitely the easiest way. So like x plus 2. And then we got 2 absolute value of x plus 1. And then minus 2. And then we can see they are crossing at 2, 4, and then negative 2, 0, just like we had anticipated. Okay. So these last two ones, hopefully you've seen enough that you can give them a try now. Again, we do need to check for extraneous solutions, and I'm okay if we just use Desmos for now, as long as you know how to do it by hand. That is important to know. But that all being said, let me know if you guys have any questions. I'd be happy to help. Thanks for watching.